Hi everybody, welcome to another video in statistics. We continue chapter 5, probability. Section 5.4, conditional probability and general multiplication rule. So this is still multiplication rule, but more general. So first, we define conditional probability, the notation P of F given E. So it is read the probability of event F given that E already occurred. It is the probability of F occurs given that E already occurred. So the second one after the vertical line is the one that already occurred. Then the probability of the first one. Right, so let's see how it works. And suppose a single 6-sided die is rolled. Suppose that it is a fair die. The probability that it come out 4. So a die with standard fair dice have 6 faces from 1 to 6, and we get 4, which is 1 out of 6. So probability of getting 4 is going to be 1 out of 6, because a die has 6 faces, and if it's fair die, the probability it land on each face will be equally likely, and so we have 1 over 6. Now suppose that the die is rolled on the second time, but this time we told that an outcome will be an even number. So now we know that the probability of getting a 4 still, but this time we know that it is an even number. So what is the difference here? So if we go back to the previous part of the problem, so if we have, in this case, the probability of getting a 4, first we're going to list everything in the sample space. 1, 2, 3, 4, 5, and there will be 6 of them. And the event here is getting a 4. So that is 1 out of 6. Now in this case, the sample space is still that, but we know that it's going to be even. So the probability of getting even, or the event of getting even, is 2, 4, and 6. And out of those, the probability of getting a 4 is just 1. So in this case, if we know that it is an even number, and so we only choose 1 out of 3, the 4 out of 3 even number. So the probability of 4 given that it is an even number is 1 out of 3. So that is conditional probability. So there's a formula for it. It says that if E and F are 2 events, then probability of F given E is probability of E and F over probability of E, or we use N as a number. Right? Once again, this is the two-state probability. Right. So look at an example and see how that works. If suppose a group of students were asked if they carry a credit card, their responses are listed in this table. So freshman, sophomore with the credit card, yes or no. Right? If a student is selected at random, find the probability that he or she owns a credit card given that the student is a freshman. So if we want to just do this based on counting, we do that 2 different ways here. If we just count, given that it is a freshman, so how many freshmen we have? The total will be 60 freshmen in total, right? So we know that 60. Find the probability that he or she owns a credit card. So out of this 60, 40 own carry a credit card. So we have 40 out of 60. So carry a credit card, even that is a freshman. There are 60 freshmen, and there are 40 out of those 40 carry a credit card, which is 2 over 3. Now if we use the formula here, so probability of a credit card given that it is freshman equal to the second one, probability of getting a freshman, and probability of getting a credit card and a freshman, and freshman. Right. Now, getting a credit card and freshman, that will be 40 out of 100. And getting a freshman, there's 60 freshmen out of 100. Divide fraction is multiplied reciprocal. So we'll flip the second fraction. That cancel out. 14, 60 cancel out. That 2 over 3. Right. Of course, they should be the same. Now, if the student select at random, find the probability that the student is a freshman given that he or she owns a credit card. Now, this is a different one. We're going to flip. I'm just going to do for the first one. I'll just do counting instead of using this. So find the probability that it is a freshman given that he or she owns a credit card. So own a credit card is 65. And out of those, there are 40 freshmen. So yeah, just like that. If we divide by 5, that would be 8, 13. Yeah, so we just like that. So just count how many we have in a credit card, and out of those, how many in freshmen. Now, another one is a survey was conducted by the Gallup organization on Sunday, asking the question, which of the following statement come closest to you? Do you believe in God? Don't believe in God, but you do believe in universal spirit or higher power, or either. Anyway, so, and of course in different part of the country, so we have this table. Now, the question is, what is the probability that a random selected adult American who lives in the East believe in God? Right, so the difference between this table and that table previously is that this one doesn't have the total. So before we do anything, we will add the total for each category. Right. Now we have the total. Just add everything in this column. I can also use this calculator also. Right, 787. $167. $63. Now add all of them up. $10.17. That's exactly the total number we expect to get. Now we add for the total here. Of course, I can also use this calculator. 204 plus 36 plus 15. 255, 212, plus 29, plus 13, 254, 219, plus 26, plus 9, 254, 152, plus 76, plus 26, 254. If we add all of them up, let's see, 254, there are 3 of them. I'm just going to say times 3 plus 255. Yeah, so the totals are correct. That's what we have. Now, what is the probability that a random selected item who lives in the East, so who lives in the East and believe in God? I just say this is event E, F, and G. So believe in God is E. So, who live in the East is 255, and out of those, there are 204 believe in God. So just that. So 4/5, 0.8, or 80%. Yeah, so the total of people living in the East and believe in God. So 80%, just like that. Next, what is the probability that a random selected American who believe in God? The total is 787, and who live in the East. So believe in God, but live in the East. So that person believe in God, so have to be one of those 787, and live in the East, there are 204. So actually we cannot reduce it. So that is 25.9%. Right, so it's important to have the total, and then we just look for out of those how many in that total that belong to the some certain category. So that's pretty much it. Next, the general multiplication rule. The probability that 2 events in F both occur is given like this. Actually, it's not that complicated. From here, all we do is multiply by probability of E on both sides, and that cancel out. And so this formula implies this formula. So just multiply to it. By the way, at the end of this section, this chapter, there's the summary of all the formula we have. Right. In words, the probability of E and F is the probability of getting event E occur times the probability of F occurring given that the occurrence of event E. Right, so let's see. There's formula nice and all, but sometimes we just do the prompt without knowing the formula. Right, now, I suppose there are 32 chocolates in the box, are all identically shaped. 11 filled with nuts, 8 with caramel, and 13 with solid chocolate. Right, you randomly select one piece, eat it, and then select a second piece. Find the probability that selecting 2 nut candies. Remember, we kind of do this with the tree diagram on the previous one, right? So now to save space, we can also do like this. And so probability of selecting 2 nuts candy. So the first one is a nut. Is filled with nut. How many do we have? There are 32 in total. And the first one filled with nuts. There are 11 filled with nuts. the second one is also filled with nuts. Now, you select the first one, and then here's a keyword, edit. If you edit, then will be only 10 left. 10 filled with nuts left. And the total original 32, each one of them, there's 31 left. So multiply this across, we have, put parentheses around this, 11 over 32 times 10 over 31. So we have that 55 over 496, or 0.1101, or 11.01%. Right. So we just do that, or we can make a tree diagram. This like so fruit nut, caramel, and solid. And then the second one, the three scenario, get nut, caramel, and solid chocolate. And originally there's 1132, and then if we eat the first one, nut, there's 10 left, and then 31. So if we want the nut and nut, we go this path, and we multiply all the probability in that path, this number and that number. Essentially, that's what we have. Yeah. So sometimes we just draw this. Instead of draw the full tree diagram, we have all the scenarios. We just focus on this particular scenario. Right. Consider political discussion group consisting of 7 Democrats, 7 Republicans, and 3 Independents. Suppose that 2 group members are randomly selected in succession to attend a political convention. Find the probability of selecting an independent and then a Republican. So the first one is independent. And the second one is Republican. Right. So the total is 7, 7, and 3. So the total is 17. Now, I have 17. If we want one independent, there are 3. So 3 out of 17. Next, the second one is Republican. Now that we select the first one, there's only 16 left. But the first one is independent, and we did not choose Republican first, so there's still 7 Republican left to be chosen. So that's what we have. So multiply straight across. Get fraction out of this, 21 out of 272, 0.0772, or about 7.72%. Right, so just write the slot and the probability for each time. Yeah. Now this is exactly where it is independent or dependent. We just write this different slot, just find corresponding probability and multiply them. This kind of like the previous section, except the previous section it is independent event. We still multiply them though. Find the probability of select both independent. So if the first one is independent, and the second one is also independent. So the first one is independent. Again, there's 17 of them, and 3 independent. Now we choose the first one independent. There will be only 2 left, and we choose 1 out of 17, so there will be 16 left. So we end up with that, and that gives us 3 divided by 17 times 2 divided by 16, or 1/8. Can we have a fraction? 3 over 136. Zero point 0.022. Right. So it is about 2.2%. Right. Now, an ice chest contains 4 cans of apple juice, 8 cans of grape juice, 6 of orange, and 5 of pineapples. So, right. So the total: 4 apple, 8 grapes, 6 orange, and 5 pineapple. So that will be 10, 13, 23. Find the probability of select all grape juice. Right, so you suppose that you reach into a container and randomly select 3 cans in succession. So you not pick one up and then put it back. So select it one and keep. So all 3 of them are grapes. Just say, is this grape? Alright, how many grape juice? We have the 8. Originally there's 23. So we choose 8 out of 23. Now that we have it, we keep it. There will be 7 left. And there's only 26 left in total. I don't know how to do that, but 22. And then when we give 2 out, there will be 6 left out of 21. So multiplication straight across. So the top we just have 8 times 7 times 6 multiply across. 336. The bottom 23 times 22 times 21. And if we take this number divide by that number, can we simplify? Yeah, 8 over 253. Or 0.3162 or 31.62%. I'm sorry, I missed a decimal point. So it's 3.162%. Yeah. Find the probability of selecting no grape juice. Well, that's different. Still select 3 of them, and there is no grape juice on all 3 of them. Right, the total of 23, we know that. Now, the first one is not a grape juice. So originally we have 8 grape juice out of total 23. So meaning that if we don't want grape juice, that will be without the 8. So before apple, 6 orange, and 5 pineapples. We add all of them up. Or we just take 23 total minus the 8 grape juice. 28 minus 23 minus 8 is 15. So there are 15 cans that are not grape juice. Now, if you pick one, there will be 22 left. If you pick one more, there will be 21 left. Now, as for the no grape juice, if the first one original 15, when you pick one, there's 14 left. Pick one more, there's 13 left. So just do this. So we say the top is 15 times 14 times 13 and then divide it by 23 times 22 times 21, and we have that. Can we get the fraction? 65 over 253. So we have about 0.2569, so that about 25.69%. Right. Next, find the probability of select at least one grape juice. Now, similar to the previous section when we have at least one, that can be difficult. If it's at least one, we select 3 cans, right? So it could be 1, could be 2, could be 3 of them grape juice. So that more scenarios than we want to. So important things about when we say at least one, complement to at least one is none, right? Yeah, at least one could be 1 or more, and complement to that would be none. So the probability of getting at least 1G is equal to 1 minus the complement of that, which is probability of getting no G in 3 trial. Yeah, because we select 3 cans. So it's going to be 1 minus, it's exactly what we have earlier, 65 over 253. So 188 over 253, or 0.74, or 74.3%. Yeah, so at least one, the complement of at least one is none. So when we say at least one, take advantage of that, because there are too many scenarios. We could have one grape juice. Is that on the first one, or is that on the second one, or the third one? Or we might have 2, maybe the first and the second, the first and third, 2 and 3. So there are too many scenarios to consider. Right. So next, we have this game. Suppose that we have a game of select 2 cards out of 4, and you win $1 if both of them have the same color, and we lose $1 if both of them have different color. We find, okay, these are 4 aces. Let me zoom out. Right. So there are 4 cards. So the game here is we scramble it, and we don't know the order. Right. And we just pick 2 of them. Let's say I choose these 2. If it is the same color, you win. If opposite, if different color, you lose. Right, so like this, 2 red, that means you win. Try again. Right, let's pick the middle 2. Right, different color, 1 black, 1 red, that means you lose. Right, and we just keep doing that. And the question is this a fair game? Right, now let's just see. It will list out the probability. There are 2, pick out 2 cards. The first one, and could be red, So we say all the scenario will be red and red, red and black, black and red, then black and black, right? The sample space, those are 4, right? And the probability of the same color will be red red or black black. Therefore, the probability of getting event E is 2 out of 4, which is 1/2. In that case, that would be a fair game, right? Let me zoom in first. That could be the case. However, it is not. This is not a fair game. Right. Now, the problem with this is, even though there are 4 cards and you select 2, even though we pick 2 at the same time, but actually we pick the first one and then the second one, right? So, in that case, let's draw a tree diagram and see what happened. Now, the tree diagram. So the first one will, let's say we had a black card or we get a red card. The chance for that is 2 out of 4 each, right? There are 4 cards total. Probability of getting a black card is 2 out of 4, 2 out of 4 to get a red card. So that's the first one. On the second trial, probability of getting a black card, probability of getting a red card. Same thing here. Black and then red. Now, the thing is, say if we have 4 cards, doesn't matter what the first one is. Let's say if the first one is red, how many red are left? If you pick the first one, it is red, take that away. Out of these 3, only one of them is red left, right? So the chance to match color with this one is 1 out of 3. So the chance to win in that case is only 1 out of 3, right? Actually, it is 1 out of 3 now. So, but of course, we only have a few trials. If we want to get a good probability, we have to do the experiment many times. That's called the law of large number. Anyway, so if the first one is a black card and the second one is also black, there's only 1 left out of 3. And then if the red card, there are 2 red cards left out of 3. Right. If the first one is red, there will be 2 black cards left out of 3. And then if the first one is red, there's only 1 red left out of 3. Right. Even though we pick 2 cards at the same time, that is the tricky part. Even though we say at the same time, but in reality, it does not. We pick the first one and then the second one. And that changed a lot. Now, in that case, the probability of getting a black and a black is 2 over 4 times 1 over 3. So that gives us 1 over 6. Yeah, 2 and 4 cancel out. Now, the probability of getting the first one is black, the second one is red. 2 over 4 times 2 over 3. 2 and 2 cancel. That gives us 1 over 3. Right? 4 and 4 cancel. Probability of getting the first one is red, the second one is black. The first one is 2, 4 to get a red, and 2, 3 to get a black. And 4 on the top, 12 at the bottom, 1 over 3. And finally, at the last one, red and red, we have 2 out of 4 originally. After that, 1 red left out of 3. So 2 and 4 cancel out, 1 over 6. So it's true that those are the outcomes. However, this is not a equally likely event because the probability of getting them are different probability. So this is not equally likely. So the classical method like this will not work. So that is wrong, because we don't have equally likely to get those. And after that, at the end, we said, what is the probability of getting the same color? Well, the same color could be this, getting two black cards or getting two red cards, and those are mutually exclusive events. They are not overlapping, then we just add them, right? So probability of same color equal to probability of getting a black and a black card, or the probability of getting a red and a red card. Those two are mutually exclusive, so we're just going to add them. So 1/6 plus 1/6, which is 2/6, reduced to 1/3. Now that makes sense, right? So the first one, after you pick, doesn't matter what it is. This one's red. Out of those three left, only one of them red. If you pick that one, you win. If you pick something else, you lose. And then are two black cards that you will lose. And the chance you pick to win is having the same color. Right, so yeah, so I thought this is an interesting problem. The key here is this is not an equally likely event. And with that, stop the video here, and we pick it up on the continue on chapter 5 in the next video. As always, thank you for watching.